This video will cover section 2.6, related rates. In section 2.5 we talked about implicit differentiation, which is where you take the derivative of a variable with respect to a different variable. When we talk about related rates, we're looking at more real-world type problems. So most of the time with related rates, we're taking the derivative with respect to time. So it's how your position is changing with respect to time, how volume of an object is changing with respect to time, and so on and so forth. So there's that relationship between different variables. So if I am looking at the volume of a cube, for instance, as one dimension changes, as the side length changes, the volume of the cube is changing. So we have some rates that are related to each other. So when we do related rates problems, it's going to be a word problem. And most of the time with a word problem, the first thing we want to do is to draw a picture. And sometimes the picture is given to you, and sometimes you need to draw a diagram of the picture. The next thing to do is to identify the variable whose rate of change you seek, and that will be given to you most likely in the problem. And the variable whose rate of change you also know, which will be given to you in the problem. So let's look at the first example, and then we'll kind of go through the steps as we look at this first example. Okay, sorry about that. I had to figure out how to move my page. So looking at this first example, example 1, we have a 13-foot ladder is leaning against the wall of a house. The top of the ladder is moving down the side of the house at a rate of 2 feet per second, which is shown here. Typically this is not normally shown, so I would write this into the picture. At what rate is the base of the ladder sliding away from the house when the base is 5 feet away from the wall? So there's a couple of things that I would like to add here. So we have this 13-foot ladder, and the reason why we can label that as 13 feet is because it's a constant. The length of the ladder will not be changing. But the length of the ladder, from the top of the ladder to the floor, that will be changing, and also the length from the base of the ladder to the wall will be changing. So if you look at the third step, it says find a formula relating the variables. But what's important is to not substitute for the variables now, or you will freeze the motion of the problem. So I'm not going to write in my picture the base is 5 feet away because we're actually moving, and so that would not be accurate. So I'm going to call that variable x. So at any given time, that could be changing. And then also this value is changing, so I'm going to call that variable y. It really doesn't matter what kind of variable you use. You could use b for base, h for height. It doesn't matter as long as they're different variables and you know the difference. Okay, so we want to kind of identify everything that we know. We know that the ladder is moving down at a rate of 2 feet per second. And that distance right there, the top of the ladder to the floor, is called y. So it's y is moving at a rate of 2 feet per second. So we're going to call that dy, the rate of y, with respect to time. And if you have a hard time with your units here, just look at 2 feet per second. So feet is your y value, is the distance, over seconds is time. So you're taking the derivative of y with respect to time. And they tell us that it's moving at a rate of 2 feet per second. But what's also important is the word down. If it's moving down, then the length is getting smaller. You also represent it here with the arrow, but make sure you pay attention to that and make your constant negative. So it's at negative 2 feet per second. Okay. And what we're looking for is at what rate is the base of the ladder sliding away from the wall. So the base from the wall is x, so we want to know the rate at which it's moving. So we're going to call that dx dt. And that is what we're looking for. We don't know what that is. But we want to know how that's changing at a certain point. So I'm going to write that in when the base is 5 feet from the wall. So when x is 5, what is the rate of change? Okay, now again, I told you not to plug in values for y and x, so what you can kind of do is make another little diagram, which we can kind of call the freeze frame. So if I freeze this picture in time, at the time that I want, which is when x is 5, then you can get what your other length is. And so hopefully you would know that this is a 5, 12, 13 triangle. So I know that at the moment that the base is 5 feet from the wall, I know that the top is 12 feet from the floor. Okay, and that's going to be important information. Okay, so this is kind of all my important information, but as I think example or step 3 said, is to find a formula relating the variables. Again, related rates. You're looking for how those rates are related to each other. So I want to figure out, I've got dy dt, I've got dx dt, I've got this xy. How do all of these relate? Well, you can clearly see it here with this right triangle using the Pythagorean theorem. So I'm going to write out x squared plus y squared equals, we'll just call this z squared. We'll call the third side z. I'll write that out here. We'll call this z. Okay. Now, if I were to plug in here 5 for x, y for 12, and 13 for z, it really doesn't get me anywhere. It just gives me a relationship that's equal, and that doesn't help me at all because x is changing and y is changing. We do not want to substitute for the variables here. But 13 is not changing. So I can actually substitute, since that is a constant, I can put 13 in for z. So I'm going to go ahead and do that. So we have x squared plus y squared equals 13 squared, which is 169. Okay, so we have gone through step 3, so now look at step 4. We found the formula. Now it says differentiate implicitly with respect to time. So it says implicitly because we're taking the derivative with respect to time, not with respect to x or y, but with respect to time. So now we have both an x term and a y term that we're taking the derivative with respect to time. So the derivative of x squared is 2x. But then we're not taking the derivative with respect to x. We're taking the derivative with respect to t. So we need to multiply by dx dt. This is a little different than what we saw with implicit differentiation in 2.5. So now plus the derivative of y squared is 2y, and then with respect to t, dy dt. And then the derivative of 169 is 0. Okay, we're going to clean this up a little bit. And so now that we have taken the derivative, we can plug in our values. And now we're going to freeze frame it at the time that we want, which is when x is 5. So we're looking for dx dt. So we want this value right here. So we need to make sure everything else can be filled in. Do we know x? Yeah, x was 5. Do we know y? Yes. At the time x is 5, y is 12. Do we know dy dt? Yes, they told us was negative 2. So I'm just going to plug in all the values that I know, leaving the unknown dx dt. Also at this point, I have a 2 and a 2 in each term, so those are both going to cancel out. Doesn't matter, zero's on the other side, so those are going to go away. So x is 5, so we have 5 dx dt plus y was 12 times dy dt is negative 2. And then we can solve for our unknown dx dt. So that'll be 24 divided by 5. It's a positive value. You always want to make sure that your answer makes sense. So if the ladder is moving down, then the base is moving farther away from the base of the wall, so therefore we would be increasing. So our rate is positive, which means we're increasing. So you always want to remember units. So this is feet per second. And actually, we're not finished. With related rates problems, this is actually not enough. So welcome to calculus. You've got to learn how to write your answers in complete sentences, or at least complete thoughts. So if you go back up and you look at the last step, solve for the rate of change, done, and give a summary sentence including direction, whether it's increasing or decreasing in units, or in this case, whether it's moving away from the wall or towards the wall. So we need to actually write a conclusion sentence here. And you're basically going to go and regurgitate the problem. So the problem says, at what rate is the base of the ladder sliding away from the house? So we would say the base of the ladder is sliding away from the wall at a rate of 24/5 feet per second. And then you also want to make sure, this is still not enough information, believe it or not. You want to state specifically when. When are we talking about? Are we talking about at time 2 when it's 10 feet down from the wall? Well, we remember the problem said when the base is 5 feet from the wall. Or when the base is 5 feet away from the wall. Okay, I know this seems like a lot to write, but if this is something that you're really going to have to get used to for the AP test, is writing your answers, especially with these types of word problems. So you need to make sure you include as much information as possible so that you'll get full credit for explaining your answers. So that's our first problem. This is a very basic related rates problem. So we're going to move on. We're going to try a different type of example. Okay, example 2. This is another very classic problem. So you have a cone and water is draining out of that cone. So most of the time, again, they won't give you a picture, but I've drawn an inverted conical tank here for us. So we've got water in this tank, and it is draining. That's our important word. We always want to make sure we know which direction. Is water being pumped into the cone or the tank, or is it being drained or leaking out? So that's important. So draining at a constant rate of 10 feet cubed per minute. They just gave us some important information. Water's draining. So what is that? Feet cubed, we're talking about volume. So I'm going to include in my picture here that water is being poured out, and I'm going to label that volume, or dV dt, is changing with respect to time. So our volume is leaking out at a rate of 10 feet cubed per minute. Since it's leaking out, that's negative. So that's something you need to watch out for. Okay, so there's one rate that we have. And then they give us some more information. If the tank is 8 feet across the top, so we have our diameter is 8 feet. And 10 feet deep. Find the rate at which the depth, so now they're asking you what to find, the rate at which the depth of the tank is changing when the water is 5 feet deep. Okay. Now again, with your variables, you can choose whatever variables you want. I like to go with what is in the formula that is going to be relating our rates. So we're talking about width and height and volume. So we're talking about volume of a cone, which is going to be the equation 1/3 pi r squared h. Sometimes the problems give this formula to you, but I would consider it a good idea to memorize this formula, and the volumes really of most of your basic shapes. Okay, so we see that first of all we have the radius here, and they gave us the diameter, so that's something that you want to make sure and not mix up. So we're going to just look at the radius. So 1/2 of 8 would be a radius of 4. Okay, now we have our equation and we have our diagram and our relationships, and let's see what they were looking for. Okay, the rate at which the depth of the tank is changing. So the depth of the tank, we're talking about the height here. So I'm going to use the variable h and r and v. So if I'm talking about the depth of the tank or the water in the tank, I'm really looking for dH dt. So we want to find dH dt when the water is 5 feet deep. So I want to find this when the height is 5. Okay, so that's what we're looking for. We have all the information that we know. Now we need to take the derivative using implicit differentiation. But if you stop right now and you think about this for a second, if I were to take the derivative of this, v would be dv dt, which we have. And then when I take the derivative of r squared and h, I have two separate variables. I'm taking the derivative with respect to t. So what's going to happen is I'm going to have a dr dt and I'm going to have a dH dt. dH dt is what I'm looking for. dr dt, however, is unknown and not what I'm looking for. So that's going to pose a problem. So what I want to find is I want to find a relationship for R in terms of either the volume or the height, really the height, so that I can now have this all in terms of H only, so that I can take the derivative and it will only be in terms of H. So that's going to come from our diagram over here. Because at the time when the height is 5, so let's say I've got water here, and the height of that water in the tank is 5 feet. Then what is the radius? Okay, it's just a simple proportion. So if you look at the proportion here that's related is 4 to 10. So at any given time, the radius is related to the height in a ratio of 4 to 10, or if you wanted to say 2/5. So if we want to get R in terms of H only, then we would say that's 2/5 H. And then we substitute 2/5 H in for our R. Okay, so now we're going to replace that. So we get the volume equals 1/3 pi times 2/5 H squared times H. Let's simplify that down. And we get, if you simplify all of this down, so hopefully you can do that on your own, then what you get is 4/75 pi H cubed, once I simplify that. Okay, now, I still have not taken a derivative yet. All I did was get my volume in terms of H only. And again, I want to do that because I want to find dH dt, so I want to have my equation in terms of H only. So now let's take the derivative with respect to t. So derivative of v with respect to t is just dv dt. Now, 4/75 pi, just a constant, so it's going to stay 4/75 pi. Then I multiply by the derivative of h cubed. Remember, we're taking the derivative with respect to t, not h. So that's going to be 3h squared, then times dH dt. Okay, at this point, we can plug in what we know. So we know dv dt was -10. And if I clean this up again, 475 times 3, that's going to be 4/25. And then h, we said they wanted it at the time that h was 5 feet deep. And then we're looking for dH dt. So we have everything except for dH dt. Okay, so if you solve that, and again, make sure, I would go ahead and pause the video here and solve yourself, and then come back and make sure that you're getting the same answer that I'm getting. Okay, I got -5/2 pi. Hopefully you got the same thing. And then we want to include our units. So remember, the rate that they gave us was in feet cubed per minute, but we're talking about a height now, which is only one-dimensional. So we're going to say feet per minute. Okay, and again, last thing that we want to do is to write our conclusion statement. So what I want you to do again is pause the video. I want you to write your conclusion statement, and then check back with me and see if you get roughly the same thing. Okay, so I have written the depth of the water is decreasing at a rate of 5/2 pi feet per minute when the water is 5 feet deep. And I want to mention something that you probably didn't do, or I probably did different than you. First of all, you probably noticed that I didn't put a negative here in front of 5/2 pi. And the reason why I did that is because I put the word decreasing. So you might have said the depth of the water is changing at a rate of -5/2 pi, which is fine, but this is actually considered better. You need to understand that when you say decreasing, that's a rate, and it's saying that the rate is a negative rate. So if you say the word decreasing, you do not have to put the negative here, because that's like a negative, a double negative. Okay?